Hello friends, today I will discuss about ideal gases and non-ideal gases. Firstly, in ideal gases, we are discuss about in details. The ideal gases are in Raoult's law. It depends on. Next is it is the gas composed of many randomly moving point particles that do not interact except when they collide electrically elastically. And firstly, Raoult's law, the mathematical expression for the Raoult's law, PV is equal to nRT, where P means pressure, V means volume, N means number of moles, R means gas constant, T means temperature. A gas behaves more like an ideal gas at higher temperature and lower pressure. Next point is Raoult's law. Potential energy due to intermolecular forces become less significant compared with the particles. That is, kinetic energy and the size of the molecules becomes less significant compared to empty space between them. Next is the ideal gas model tends to fail at lower temperature or higher pressure when the intermolecular forces and molecular size becomes important. Next point is the it is also fails for most heavy gases such as many refrigerants and for gases with strong intermolecular forces, notably water vapor. Next one is the ideal solution means an ideal solution is that solution that follows the Raoult's law under all standard temperature and concentration. It satisfies that delta V mixing is equal to 0 and delta H mixing is equal to 0. We can also say that it is the solution of two components A and B, which is the A to B interaction are of the same magnitude as A to A and B to B interaction. Next is the only solution with low concentration of solute behaves ideally. For example of the ideal solution, benzene plus toluene, that is the volatile component. And second example of the ideal solution is chlorobenzene and bromobenzene. And second point is non-ideal solution. Non-ideal solution is the solution which do not follows the Raoult's law of the non-ideal solution. That therefore delta V mixing is not equal to 0 and delta H mixing is not equal to 0. This is the non-ideal solution. It is the solution in which solute and solvent molecules is interact with one another with a different forces than force of interaction between the molecules of the pure component. For example, the sulfuric acid and water. The sulfuric acid as a solute and water having a solvent. The amount of heat is evolved is larger and thus change in volume is also seen. Next point of this point is the deviation. There the deviation there so deviation that are two types. First one is the positive deviation and second one is the negative deviation. The positive deviation having in mixture showing a positive deviation from Raoult's law, the vapor pressure of the mixture is always higher than you would expect from an ideal mixture. In diagrammatically vapor pressure versus mole fractions, that is the vapor pressure of compound pure A compound and vapor pressure of pure B compound. Vapor pressure is the actual vapor pressure and ideal vapor pressure. That is the mole fraction is the component A having 0 to 1 and component B having 1 to 0, that is in diagrammatically. Next, in the deviation can be small in cases with a straight line in the last graph turns into the slight curve. Next is the notice that the highest vapor pressure anywhere is still the vapor pressure of pure A component. Cases like this where the deviation is small behave just like ideal mixture as. And second, but some liquid mixture have very large positive deviation from Raoult's law, and in these cases the curve become very distorted. And second is the mixture over the range of component have a higher vapor pressure. that is than either pure liquid, the maximum vapor pressure, that is the higher vapor pressure having the maximum vapor pressure and no longer one of the pure liquid. In diagrammatically vapor pressure versus mole fractions, that is the vapor pressure of component A and second component is the B, that is the actual vapor pressure and ideal vapor pressure is higher. And in this diagram, next point is explaining the deviation. First, the fact that the vapor pressure is the higher than ideal in this mixture means that molecules are breaking away more easily than they do in the pure liquid. That is because the intermolecular forces between molecules of A and B are less than they are in the pure liquids. We can see that when we mix the liquid, less heat is evolved. When the new attraction are set up, then was absorbed and break the original ones. Heat will therefore be absorbed when the liquid mix and enthalpy changes of the mixing the end point. Next point or the last point of the deviation, the classic example of mixture in this kind is ethanol and water. In the example of the positive deviation, this produces a highly distorted curve with a maximum vapor pressure for a mixture containing 95.6% of ethanol by the mass. And the second type of the negative deviation, in exactly the same way, you can have mixture with vapor pressure which is less than would be expected by Raoult's law. In some cases, deviations are small, but in other they are much greater, giving maximum value of vapor pressure lower than that of the either pure compound. That is the vapor pressure versus mole fraction, and in diagrammatically vapor pressure is the lower. Next, explanation of the negative deviation. These are the cases where the molecules break away from the mixture less easily than they do from the pure liquid. New, stronger forces must exist in the mixture than in the original liquid. We can recognize this happening because heat is evolved when we mix the liquid. More heat is given out when the new, stronger bonds are made than was used in breaking the original weaker ones. And last one is point of this explanation, they involve actual reaction between the two liquids. For example of the negative deviation is nitric acid and water. The two covalent molecules react to give hydronium ions and nitrate ions. In the reaction, water plus HNO3 to give the H3O plus NO3 minus, that is the hydronium ions and nitrate ions. This is the negative deviation. Thank you for